Hi everyone, welcome. My name is Bianca Fortuna, and today I'm going to speak to you about model explainability and interpretability with a focus on how to use some of these methods and tools in practice. So today we keep hearing about machine learning models and artificial intelligence making breakthrough, solving problems that were thought impossible maybe a few years back. And we have these really great, remarkable, highly accurate models that we're putting more and more into production every day. But when these models actually go into the real world, we need to start asking a lot more questions. Can we trust this model? Can we actually rely on them to make stable and reliable decisions every single time they are being used? Do we really understand how these models are behaving when we put them in front of human beings and when these decisions are actually marking their lives? So with that in mind, I want to discuss this topic of model interpretability. And I feel like this is a very, very interesting topic because interpretability is something that's being used more and more in the machine learning circles. But I don't think there's a very strict definition of what interpretability is. But there are a few words that get mixed or associated with this idea of model interpretability. And the first one is this idea of explanations. So when you think of making a model interpretable, a lot of people think straight away of having some explanations associated with model predictions. And these explanations are very important because in a very specialized domain, such as healthcare, for example, if you have a model predicting that somebody has a specific disease, you will definitely want to know why the model has done that prediction, and is there anything you can do for that prediction maybe not to come true if a disease is involved. On top of that, it's very important that these explanations are easy to understand by humans. So if you think of my previous example, of predicting if somebody is going to have a disease, it's very important to understand this explanation in order to actually take an action based on them. So for example, age or like other risk factors in that particular scenario. Now imagine the opposite end of the spectrum, where maybe you don't have this easy to understand explanation, but you have 100 columns with very weird names like column 1, 2, 3, and 4, and a lot of like floating point numbers around. Are you actually going to be able to understand those variables and how they actually impact your model prediction? I would say no personally, or not without a lot of work from your side. Another very important characteristic that is often associated with this idea of interpretability is transparency. So transparency in the machine learning model is about truly understanding the mechanism of the model and how that model works. So you'll be able to like truly predict the model behavior in the real world. So you actually know what actions to take. Then is this idea of trust. Do you actually trust the model? Do you know when the model is going to go wrong? And do you actually believe that this model is going to take unbiased decisions that are going to probably impact people's life in some cases? The last thing I wanted to mention here is this idea of causality. So causality is not necessarily always associated with model interpretability, but I think the idea of causality can sometimes come from this explanation. So a lot of the time we hear correlation doesn't imply causation, but people intuitively make that association between something that happens with like in the explanation, and they can associate that with this idea of causality. And that association sometimes can be very tricky, and it needs to be handled with care. So a lot of these methods and tools that I'm going to talk about today have a lot of benefits, but they also have a lot of limitations. So it's very important to understand them all when using them in the real world. So the next thing I wanted to touch upon and clarify is some model interpretability terms. So these terms are becoming more and more common when talking about model interpretability, and just wanted to clarify a few of them today before I jump straight into them. So the first one is the idea of a glass box versus black box interpretability. So a black box interpretability is interpretability on top of models that are already in a way explainable or interpretable out of the box. So think about something like a linear regression or a decision tree. Based on how that model is trained and the model is built, you can intrinsically understand what the model is doing. So that's in a way like transparent characteristics. Then you have this black box interpretability, which are interpretability techniques put on top of any type of model. And you don't really need to understand how the model was trained, but you're just essentially looking at how that model is behaving. Then you have local versus global explanations. So local explanations are explanation about a single prediction or of area of predictions, while global explanation is about understanding the global behavior of the model as a whole, rather than individual local perspectives. Model-agnostic versus model-specific refers to different type of techniques. So there's some techniques that apply to any type of model, as long as they have maybe an API, for example, that you can use to actually query that model. It can be applied on top of any model, regardless of the model type. And others are model specific. So for example, there are a few techniques that only apply for neural networks. So those would be the difference between these two terminology. And the last thing I wanted to cover is this idea of explanation coverage. So when we talk about explanation coverage, we actually mean the region in the input space where that particular explanation applies to. And hopefully we'll get a bit more clarity on that as this talk progresses. So I really wanted to just touch upon about this question, because I think it's a very interesting thought experiment. So if I read you this list of different type of machine learning algorithms, which one would you say are interpretable? So k-nearest neighbor, linear regression, neural network, decision tree classifier, support vector machine. And I think like straight away, a lot of you might think, oh, okay, there's a few very obvious ones here, stuff like linear regression. Like we can very clearly look at a trained linear regression model and identify the parameters associated with every single feature, and we can interpret that. A lot of the time, true, that is possible. If we have very well understood and maybe a limited set of variables. But now think of the other scenario where you have, hundreds of variables, even though you have the parameters associated with every single one. How long and how much effort do you actually need to put understanding the interaction of this variable to fully be able to get a good picture of what this model is doing and how it's going to behave based on your input variables? So just a bit of a food for thought here. Next part is this idea of a local. The focus of this talk is going to be on local methods, black box, and model agnostic interpretability. So without further ado, let me introduce to you the first technique we're going to cover today. So this technique is called LIME, and LIME stands for Local Interpretable Model Agnostic Explanation. So what does this technique do? So the purpose and the goal of this technique is to identify an interpretable model over an interpretable representation that is locally faithful to the classifier. So there's a couple of things here to unpack. So first is this idea of an interpretable model. So we're going to see a few examples of that a bit later on in the talk, as well as what does it mean to actually have an interpretable representation. Locally faithful, that means that this explanation that we're getting is only valid in this sort of local area that this prediction that we're looking at is actually happening. So LIME works in the following way. We have an input. So this input is essentially a data point that we want to get a prediction for. We take this input and then we perturb the inputs a little bit, and then we get this perturbation and we weight them by the similarity to the inputs. We then extract the model predictions for this input perturbation. We train an interpretable model, in this case it's a linear model, on top of those model predictions, and then we construct some explanations. So more visually, what does this mean? So let's imagine we have this decision boundary here. In this case, we are facing a binary classification problem where we have two classes. We have the red crosses and the blue dots. So the red cross is the prediction we're trying to explain. So as you can see, we perturb this input where we get a lot more crosses and some dots, and they're more they're like bigger and also more emphasized in this picture based on how close they are to the input we're trying to predict. And then we are essentially just building a linear model here. So this is this dotted, this dashed line here, and this is the model we're training to explain this prediction. And as you can see, this linear model is actually quite relatively faithful to the small local region of the area we're trying to predict here. But as you can tell, there's quite a few assumptions and limitations that we'll have to deal with in this particular scenario. So the next technique I wanted to talk to you about, also just very quickly introduce it, is called anchors. So anchors is a technique in a paper that follow up lines. So this line, the same authors actually came up with this technique. And this technique is about getting to a rule that essentially anchors that prediction locally, such that in instances where the anchors hold, so the anchor is true, the prediction is consistent. So rather than trying to build this sort of model that is faithful pretty much like in a local manner, you're just looking at these rules that whenever this rule holds, the prediction is always the same. So you can actually trust it. So the way you would do this is that you would generate potential anchor candidates. You would identify the candidate row with the highest precision. Then you would ask the question, does this current anchor meet the anchor definition? So does it have high precision and highest coverage that you can in that particular area? If the answer to that is yes, then you identify the anchor and you sort of terminate the search. And if the answer is no, then you go back to the beginning and start generating some new potential anchor candidates. So to contrast this with Lime, this is what is happening. So if we look at the left-hand side image, we can see that the prediction we're trying to explain in this case is the cross. The line model is a line very close to that, is not very faithful to the decision boundary in this particular case. What the anchor does is getting this row. So the anchor in this case is this sort of rectangle box with the dashed line. And that anchor, as you can tell, would give you the same blue prediction almost in that entire area that is covering. And then D in this case is essentially the perturbation distribution that you're looking for. So very similar to what we talked in the past. As you're perturbing the input, you want to find this local area within that particular region. And in a very similar way, on the right-hand side, you can see a very similar perturbation region for the dash and the anchor and the line model associated with it. So you pretty much get the idea visually. For Lime, you build this sort of linear model that's trying to split your decision boundary, while for anchor, you're finding this sort of stable prediction area within that local region. Okay, so now that I sort of very briefly conceptually covered these two techniques, just wanted to come back to practical uses of both of them, because I did mention this idea of perturbation and interpretable representation. So I wanted to take different type of data and go through these use cases so you better understand how to actually use these techniques for your data type. So the first type of data we need to look at is tabular data. So the way you obtain perturbation for this is to fix some of the features, so don't change that at all, and then you sample the rest of the row from the values you have. And in that case, again, you'll come up with sort of different values for the input, and you'll get a better picture about your model behavior locally. And then the interpretable representation for tabular data is features in your data set. Okay, if you have images, how would you come up with this perturbation? So this is where it becomes actually quite interesting. So for images, you would use another algorithm to extract this idea of superpixels. So superpixels are like parts of an image. So think about like taking an image, doing some sort of segmentation on top of it to identify different areas of interest. And to perturb that, you essentially turn them on and off. So for Lime, the experiments they ran, this on and off would mean that you replace the superpixels, which are regions of the image, with some gray, would like just you'll gray them out. While for anchors, what they actually did is they replaced them with parts of different images. So these create different types of perturbation. And in the interpretable representation, what you're actually doing is you're activating or turning off this superpixel. So if you think about it, if you have an image classification, so for example, if you're trying to find a cat or a dog on an image, what this explanation should do is show the superpixels in that image that contributed to that particular prediction. So if it's a cat, you'll want to see like a cat face and the ears, the cat body. You wouldn't want to see something like a car or a tree, because like clearly your model is not behaving as it should in that particular case. So the next data type that I wanted to cover is text. So the idea of text classification, so you have a piece of text and you want to say what that text is about. So the way you would do a perturbation in this case is that you would fix some of those tokens and replace the rest by some random words. And the interpretable representation of this is then the presence or absence of these tokens. Tokens are words in this case, of the particular sentence. So it's like quite similar in concept to the other data types as well. Great. So let's quickly cover some of the pros and cons of these two methods, so you have a much better idea of when you should use it or not. So the first pro of these two models is that they're Python packages, so they're actually very easy to use with existing models. You just require your models to have an interface, so very similar to, if you have an interface similar to scikit-learn interface, then everything will work pretty much out of the box. It's going to give you an intuition about the model behavior locally. So that is very important when you actually work in industries or on problem sets where you actually need to understand what's happening, so you can trust that prediction when you're deploying it in the real world. Is going to help model understanding before development. So again, this builds into this idea of stable models and trusting it and understanding what it does. And it's also an additional model validation tool to existing methods. So again, it just like builds up on this idea of understanding your model behavior better. In terms of limitation, so specifically when it comes to Lime builds a linear model. So there's a local boundary that you're sort of trying to predict. But in a lot of cases, we've seen some of the visual images before, this can be highly nonlinear. Lime doesn't return any coverage information. So I think that is an issue, and that's something that, for example, the anchor technique comes and sort of solves. But the reality is that in practice, they work very well for some example, but definitely they don't work well for all examples. So a lot of like trying and error and experimentation is needed here. They don't really provide, these two techniques don't really provide a global understanding of what the model has learned, but they do like give in the papers a few idea of how you might start to get that global understanding, but they don't really offer it out of the box. And you also need a perturbation distribution to be defined for every domain. So they do have samples for like tabular and text data, and I think image data in some cases, but a lot of the time you might need to create additional, like to write additional code in order to be able to use them. Okay, so in terms of practical tips, a lot of people talk about using this to actually provide these very like stable, trusted explanations for the models. And I don't truly believe that they're there. Like, I think they should be used to provide some sort of guidance information, but they're not always 100% accurate. So you don't really want to include a lot more misinformation and uncertainty in sort of your model deployment pipeline. But what I would say this could be very, very good, well used for is for model debugging and validation, and helping you as a model developer understand what your model is doing, how to monitor your model, and when you need to detect that a prediction is wrong and what to do in that particular case, and how to retrain your model and make it better with every pass in the real world. So I think for these, that is very, very important. Perfect. The next thing I really wanted to sort of briefly touch upon is Interpretaml. So Interpretaml is a unified framework for modern interpretability. So it's an open source project from Microsoft. It's available on GitHub. And the reason why I really like it is because it does get some of these techniques together into a unified interface. So you can use different type of models in the same way, and it will compare the results together, and it provides some very nice visual tools that can help you better understand what the model is doing. And that can be very, very, very helpful when you're trying to do this model debugging validation during the experimentation and development phases. So without further ado, I would love to walk you now through a few actual examples, talk through them, and show you how these models look and how we can use them in practice. So hopefully this will all work. Okay, so let's start with Lime and anchors. So as you can see, what we're going to do here is that we're going to take some very default Python libraries and train a model, and then we're going to try to explain it. So for this particular data set, for this particular task, we're going to start with the iris data set. So as you know, like the iris dataset is like pretty common. So you have 3 classes in this case. So you're trying to predict the class of this particular flower based on the sepal length, the petal length, the width, and it's like used very commonly for example. So what we do is that very typically we start with our data set, we split it into a train and test set, and then we trained a gradient boosted classifier on top of it. So if you remember back into our earlier discussion, a boosted classifier like builds an ensemble of decision trees, in this case 20. So it's a glass box type of model in the sense that you can actually take these trees out and try to understand the decision boundaries, and this is gonna give you an idea of what the model is doing and what has learned from its data. So if we look at the model metrics themselves, we can see that this model is actually pretty good. So for a lot of the cases, it's detecting the right class, it's only making one mistake, which pushes the model accuracy, precision, and recall to 97%. Again, this is a toy data set, so in the real world, we don't really have these crazy numbers. But what we can do then is that we can actually plot the feature importance. So this is a decision tree. So with decision trees, we can extract the model importance features, and we can see here the coefficients for the 4 features we have. And in this particular case, and I really apologize, you can't see these in a lot of perspective here, but the petal length in this case is the most important one, followed by the petal width, which is quite important as well, and then the sepal length and width are not that important in themselves. Okay, so this is the feature importance for the gradient boosted classifier are something that come default with this type of algorithm, but we really want to understand individual predictions and what is happening there. So if we're looking at Lime explanation, and as I said, this Python package is actually relatively easy to use. We just import the Lime package, you just pip install this, is relatively easy, and then you use this Lime tabular explainer. You pass in your training data set, your feature names, your class names, and then we choose this sample that we want to predict, and we get the explainer that we built, which is this Lime tabular explainer, and then we say just explain in this instance. This is the model probability interface that we have here, and we say just show us the two number of features that are the most important. So if we look at the results here, it has this visual representation of what's going on in terms of Lime. So we can see the prediction probability for the 3 classes that are possible. So Setosa, versicolor, and Virginica. And we can see in this case, the prediction probability for Virginica is the highest. We can see the feature and the value for this particular case. And then we can see the 2 options here, not Virginica and Virginica, so we can see which ones they contributed to which classification. So here it's a very straightforward example, is basically saying that these 2 features contributed to this positive prediction, and there's no like other features that sort of pulled it the other way. So normally if it was a more complicated problem, you would have features that sort of push the prediction into one direction and other features that contribute the other way, and then you'll be able to see the mix there, but this is not the case in this particular scenario. So if we are looking at anchors, so as I said, like anchors is the next, in a way, the next iteration of Lime, but it's probably not as well known and is probably not as well used within industry, but it is used in a very similar manner. So again, you just install this, you pip install this, you create a tabular explainer, very similar to what we've done with Lime previously, and we're predicting the same input data as we had before. And in this case, again, we mentioned this idea of coverage for anchor and precision. So we want an anchor to have very high precision and high coverage. So like that bounding box that we saw, we want it to be as like big as possible and cover as much of the input boundary as we can. So in this particular case, we found this anchor, which is like a pretty big one. So it has petal length smaller than 5 and sepal width smaller than or equal to 2.5, and the petal width smaller than 1.2, and the sepal length bigger than 5.1. So in this case, the precision is 1. So whenever we have an input that sort of ticks all of these boxes here, a lot of the time the prediction is going to be consistent. So I think in this case it was Virginica, and then the coverage in this case is not is 0.09, so it's not very big because this is a very specific, as you can see, there are very specific characteristic here. They also have this idea of like a partial anchor. So like if we take, so as you can see, this has like 4 conditions, but let's say we remove some of this condition. So if we want to look just what happens if you have this 2 first condition, like is that this prediction of Virginica like stable, or like there's other variations that we need to take into account here. And here we can see that this gives a partial precision of 0.6, so like that goes down a little bit, but we have a much wider coverage of the area as well. So this I think this like shows you how you can use this tool to better understand your input decision boundary, what your model is doing, and how you can how is it going to behave under certain conditions. Great. So this covers the Lime and Anchor Python packages. And the other thing I wanted to show you is Interpretaml and the tooling here. So this is one of the default notebooks that they have on their GitHub page. So it's actually very easy. I just ran it before to like quickly show you, but you can go on GitHub, download this, play around with it, and understand what it's doing, which is actually pretty cool. So here again, we're using a very common data set. So this is the adult census data set where we're trying to predict if an individual income is below or above 50K. And we are using some of the sklearn tooling to do the train and test split. In this case, so we have 80% training data set and a 20% test case. So here we're building a random forest classifier. So it's still a tree-based ensemble. It's just slightly different from what we had before, and then we're fitting this, and then we want to actually plot the curve, the ROC curve of this model, and show the performance here. As you can see, these are some of the visualization tooling that's available with Interpretaml Python package, and they have some really nice graphs that come out of the box. I mean, you can see what I can do with Lime before. So I had some really like very basic visualization, and if I wanted more, I will have to go and do myself. But now with this package, they sort of come out of the box here. So we can, again, this is like an interactive graph, so you can see the thresholds. This is the ROC curve, but also you have the sum of the absolute residual here plotted against density. So again, you can interact with this how you want, and it's going to give you a much better idea of your model performance. Now I wanted to use Lime, the Lime implementation from this particular library to do a local explanation. And the reason I wanted to show you both is because this is hopefully going to give you a good idea of what's the difference between using Lime, which is the same technique, but as part of this unifying framework, and Lime on its own, and what is the advantage of disadvantages of doing that. So in this case, we're using the Lime implementation of Interpretaml. And again, we need this Lime tabular that I've shown you before in the other notebook, and we are picking an instance to explain here, as we did previously as well. And we just say Lime explain local. So if you remember, if I go to the other notebook and I scroll up, this is my Lime output. It's very simple. You can see what's going on, but there's no interaction or anything happening. While here, I can, you see there's no summary, but I can go and select some of this, like some of the like predictions in the residual. So if I click on one, hopefully this is gonna, I can see that the prediction here is 0.4. So this is the prediction probability of income above 50K. So in this case, the prediction was 0.4, so that will go into 0, and the actual is 0. And here we can see the intercept, the capital gain, native country, and like essentially everything that sort of contributed to that prediction here. It is slightly different visualization, so I think you need a bit of like a custom to understand what's going on here compared to the previous visualization that you get with the Lime package itself. I also wanted to show you one of these global explanations. So one of these global explanation techniques is this idea of more sensitivity, and you can get the summary here. Oops. And so you can see the convergence index and like the age. So these are like basically the features that contribute a lot, and like you get them ranked to sort of understand which one is more important for like for your model and how it skews it either way. Yeah, and lastly, you also have this idea of partial dependence. That is another way of explaining the global behavior. So if we look at age, for example, you can see like different characteristics of this as well. You can see the average response for age and this different distributions here. And as I mentioned before, one of the advantages of this particular tool is that you can get these and you have this like quite nice dashboards where you see the data and you can try to compare them. So you can see your available explanation for this particular one, and here you can look at again performance. So let's see if you that we had it before, like global explanation selected here, and like sort of compare them together, see this side by side. You don't have this overall graph here for partial dependence technique because it's not available in this particular scenario, but if you're using a different one, you'll probably have it there. And then we also have this local one, but in this case we only have Lime, so it's not going to be anything to compare with it with. But if you use a different one such as Shop, for example, you'll be able to compare them together and see the results side by side, which is very good. Yeah, so hopefully this helps give you a better idea of how to use this technique in practice and how they would be useful for this idea of model debugging, validation, and just essentially understanding what your model is doing and how it's behaving now and how it's probably going to behave when it's going to be deployed. So now if I go back to my presentation, yeah, these are like the examples I wanted to ask. I put a couple of resources here because I think they're quite useful. So hopefully we can get this shared with you after this talk. But they do cover different papers or resources you can go to find out more. I would definitely suggest reading Lime and Anchor papers. They're like very intuitive and informative, and is going to give you a much better feel of what the actual technique is doing, and hopefully that's going to lead to a better understanding of how to use them in practice. So yeah, this is all for me. Thank you so much for listening and spending some time with me today. And yes, it was lovely chatting to you about model interpretability and explainability. And if you want to get in touch, please get in touch with me on Twitter or on LinkedIn. I'm more than happy to chat about this subject with all of you and answer any of your questions that you might have. Thank you.